Okay, today is March 22nd, and today we're gonna have an exam. March 20. I'm gonna start here. March 22nd, 22. So what we're gonna cover today, going back here to the syllabus, is going to be current and resistance. Chapter 26 of the book. 26, current and resistance. Okay. To understand how current is generated in a metallic wire, in the metal, specifically wires of copper, we must go back. We must go back to the model of the atom. Okay. The atom can be thought of being made of a very small nucleus, very small nucleus, positively, very small, small in size, okay? Small in size. A very small, positively charged nucleus. This nucleus is composed positively charged nucleus surrounded by orbiting electrons. This nucleus has positive and neutral charges inside it. The nucleus is much heavier than the electrons. A single proton is 1800 times more massive than a single electron. It's much heavier, right? So you do the math, right? Each atom in general has the same number of protons same number of protons and electrons, unless the atom is ionized. Unless the atom is ionized, it has the same number of protons and electrons. The number of neutrons is also almost the same as the number, not always, okay? It's almost the same as the number of protons. They differ most of the time, but as a rule of thumb, we can state that it's almost the same. So we can state that the nucleus has a mass that is 3,000 approximately. That is approximately 3,600 times the mass of all electrons orbiting the nucleus. Okay? So here you go. It's n number of electrons, n number of protons, and approximately n. No, here you go. Oh, the heck's going on here? Let's try it again. Okay. and approximately n is the number of neutrons, right? So overall, the mass of the nucleus is 3,600 times more than the mass of the electron. So you can see how heavy it is, the nucleus compared to the electrons. Okay? That's why the electrons end up orbiting the nucleus. It's just like the Earth orbiting the sun. The planets orbiting the sun. The sun is much more massive than any of the planets. Even their combined mass is negligible, negligible compared to the mass of the sun. Neutrons, okay. Mass of the nucleus. Mass of the nucleus is 2n times 2n times 1800, the mass times 1800, the mass of a single electron. Okay, that's the picture that you have to have about this. Yeah.
So you say that you can relate. You say that you can relate this model of the atom to the system of
Solar system. Yeah.
So does that also mean that in that atomic scale, the gravitational force is as strong as, say, the electroweak forces?
No, yeah. What we know is that the gravitational force is negligible at the microscopic level. Okay, and we can do some math to illustrate that. The electric force is much stronger than the gravitational force. So all the time that we do any calculations at the microscopic level, we neglect the gravitational force. Okay, we neglect the gravitational force. So here you go. Here's the illustration of the atom, right? Okay, and we have electrons orbiting here, orbiting here, orbiting here, and then the outer electrons we call the valence electrons. Okay, so in this model, we have electrons orbiting the nucleus at different distances, and the furthest electrons are called the valence electrons. These electrons are the easiest ones to extract from the atom. They don't need much energy. In other words, they do not need much energy to move away from the nucleus. Can you picture that? Those are the valence electrons. These valence electrons are important for circuit. These valence electrons are very important in a given electrical circuit. Why is that? Okay, so here you go. What's happening at here you go? We have a nucleus here, another nucleus here, another nucleus here, and each of those nucleus has several electrons orbiting the nucleus. Okay. So and then we have those outer electrons. We have those outer electrons, the valence electrons, that they're so weakly bound that they can move from one atom to another. Okay, keep on jumping back and forth, things like that. That's what those valence electrons are all about, and that's what their importance. That they move freely from one atom to another. So I'm gonna put that here. These values are very important in a given electrical circuit because they can move almost freely from one atom to another, whereas the other electrons stay very tightly bound, very tightly bound to the nucleus. These valence electrons are the ones that are responsible for the electrical current. Okay? These valence electrons are the ones that are responsible for the electrical current. So let's go back to our drawing here. Here you go, the valence electrons jumping from one place to another. But that, if I put a potential energy here, a battery, if I connect the battery to this wire, what you have here is a wire, okay? A wire that I blew up, made it bigger for you to see what happens there inside. Those valence electrons, they end up being attracted to the positive side of the battery. Okay, that's how you have to visualize this thing. So electrons are responsible for the electric current, and in this drawing, they move like that. They are attracted towards the positive side of the battery. Okay, between the plates of this battery or the electrodes of this battery, we have a chemical power plant that separates the negative charges from the positive charges. When the electrons are separated and they are put in this negative side of the battery, now we have the regular electrical force to propel the electron in the circuit. Again, they go through the wires here, come back to the positive side, and everything repeats all over again. Okay? That's the idea you must have of an electrical circuit. So, so here is a source of energy, right? And here, this wire is a source of electrons. So let's write it down. Okay, so when we connect a battery to a wire, the positive side of the battery attracts the valence electrons, producing a current, an electrical current. An electrical current. What does it mean, electrical current? In other words, a current of electrons. Protons don't move because they are too heavy and they are too tightly bound there to the material, as well as the inner electrons. Okay, yeah?
So in general, the less valence electrons you have, the more conductive the material.
Yeah.
Okay, because as I understand it, the atoms with the most valence electrons are the noble gases, right? And those don't conduct. Do they conduct electricity?
The noble gases?
Yeah.
The noble gases has this characteristic that the electrons are very tightly bound to the nucleus, right?
Right. They have the full
That's right.
valence.
It's more
So
difficult to
okay.
extract electrons from them.
Okay.
So it's very stable. The noble gases are very stable. The noble elements.
So you're saying that in order for the conductivity of a material to be high, there needs to be fewer valence electrons because one, they reinforce each other. The electrons reinforce their own strength, and then they need the space to be able to jump. Correct?
They let's see.
They need available space to be able to jump from one atom to another.
Yeah, yeah, and that happens, right? Because the atoms are very small, and when we put when you have a piece of metal, you have a bunch of atoms very close to one another. Okay, that's a good model, and only the valence electrons jumps from one atom to another. That's a very good model. Something like that doesn't happen with plastic. Okay, you don't have the don't have with plastic because you do not have much conductivity in there. Okay. Okay, so when you connect the positive side of the battery attracts the valence electrons, producing an electrical current. In other words, a current of electrons. Electrical current, or in other words, a current of electrons. Or in other words, a current of electrons. Okay. after combining with the positive, I call that positive electrode of the battery, come on, the chemicals inside the battery have enough energy to separate the electrons from the protons. That's a very good model. So a battery is nothing more, nothing less than a battery is a chemical power plant. Okay, separate the electrons from the protons. Once they are separated from the positive electrode. They are thrown on the side of the negative electrode, which repel the valence electrons back to the circuit. Okay, so let's going back here. We have what we have here. We have electrostatic force attracting the electrons towards the positive side of the battery, and you also have electrostatic electrons repelling the electrons back to the circuit. In between, we have this chemical power plant, this chemical machine that's capable of separating the negative electrons from the positive charges in the electrode of the battery. Okay, so three elements, right? Three simple elements. Electrostatic attractive force, electrostatic repulsive force, and a chemical power plant that separates the negative from the positive charges. Once this chemical power plant is exhausted, you run out of battery, you throw away your battery, and you buy a new one. Okay? Or sometimes, depending on the battery that you have, you can recharge it, right? There are rechargeable batteries in there. So let's see, after combining the chemicals inside the battery, so we have, here we go. So we have three different processes. Two, actually, it's two different processes. Let's put three, okay? One, electrostatic attraction of the valence electrons towards the positive electrode of the battery. Okay, a chemical power plant in between the electrodes of the battery that separate the positive, the negative, the valence electrons from the positive electrode. And three, electrostatic repulsion of the valence electrons by the negative electrode of the battery. Three different ongoing processes. Once the energy of the chemical power plant in between the electrodes is exhausted, okay, the battery no longer has any power, and you either throw it away and buy a new battery, or you recharge the older battery. You have those two cheap types of batteries, right? The one that we use throw away, and another one that the rechargeable one that you recharge it and keep on using 100 times. That's what those rechargeable batteries are all about. You can recharge them 100 times, okay? So don't expect they're gonna last forever. No, no, they don't last forever. Okay, I used to have some batteries that used to work very well. I didn't know that they had this lifetime, you know. And then one day the battery that I used to use a lot start to the rechargeable batteries no longer was holding the charge anymore. And then what's happening here? It used to work so well, right? And the woman that sold those products to me told me, no, no, those things can be recharged only 100 times. And then you throw away, buy a new rechargeable battery. But recharge 100 times is pretty good, right? Then use a single battery and throw it away. Okay, imagine that the junk, right? You used to generate by buying the regular batteries. Okay, so that's a good model that we have in mind. Okay, let's see, here we go. Another way to look at that is in terms of an electric field. Okay, here I'm telling you in terms of an electrostatic force. Negative charges are attracted to the positive terminal of the battery. But there's another way of looking at that is far more precise. Far more precise. Okay? So you have a copper wire, for instance, that's full of valence electrons. And you have positive charges there as well. Okay? You connect this wire to a battery. This end here, I say that we have a zero electric potential energy. And here you have 10 volts of electric potential, not potential energy, electric potential. Okay, I am assuming that those wires here has zero resistance. So what happens when I connect this, the ends of those two wires, okay? Okay, so what happens is something like that. You generate an electric field inside the material. Can you picture that? I'm gonna make a better drawing here. Here we go. I'm gonna copy those electric fields. Those arrows that you see right in here is an electric field. It's possible to demonstrate that mathematically, okay? But it's very difficult mathematically. So we don't do that. So what we do is just tell you that so you can believe in this model. Here you go, the electric field. And there is more. The electric field inside your wire is constant, is uniform, just like that. It's possible to prove that mathematically. Okay? And I'm gonna go to the next one. Here you go. Valence electrons inside copper wire subjected to uniform electric field. That's what happens in every wire that we have out there. Is a uniform electric field in general. Okay? In general, it's a uniform electric field that we have inside your wire powering your electrons. Here you go. Valence electrons. When you connect the battery, you have this electric field here. And I'm going to even change the color here to make it more obvious. Right? Here, I'm going to put red here. And the electric field is going to be red as well. Here you go. Delete that. We don't need that. Okay, here you go. So another illustration here of my wire. It is as though we have a buildup of negative charges here at the end of the wire and a buildup of positive charges here at the end of the wire, producing this uniform electric field. is generated. Okay. Okay, so because we have this electric field from the right to the left, we are going to have an electric force from the left to the right. I didn't illustrate that here. Let me see if I can illustrate that. Yeah, here you go. Here's the electric force. Okay. The field is from the right to the left. The electric force is from the left to the right. Okay. And it is this electric force that powers our electrons to move. It happens that the velocity of those electrons are uniform. They don't get accelerated. They don't get accelerated because you have a bunch of junk here inside. You have a bunch of non-uniformities that slow down the electrons in addition to the electrostatic attraction of the protons. That's the model that you have to keep in mind. Okay, so overall, we say that the velocity of the electrons as a whole is uniform. The stronger the force, the faster the electrons travel overall. The weaker the force, the slower the electrons travel overall. Okay, so here you go. How do we quantify the current? Okay, the current is quantified by the number of charges that crosses this imaginary gate in the wire, this cross-sectional area here. So suppose that we could count how many electrons go through this little cross-section area here. Okay. So we have this little green man here observing, counting how many electrons go through it. It's going to be the number of the electrons, the charge of the electrons in the amount of time. That's how we define electric current. Delta Q over delta T. Okay? So let's document what we just said there. Okay, once the energy of the okay, so here we go. So inside a wire, we have these valence electrons. When we connect a power source to the wire, okay, we generate a uniform electric field in the axial direction of the wire. Okay, when we connect the power source to the wire, power source means a battery or power supply. This electric field produces a uniform force in each electron. A uniform electric force in each electron. It is exactly the force that powers the electron in a wire. In principle, these electrons were supposed to be accelerated because they are subjected to a constant force, right? In principle. But something that doesn't, but something like that doesn't happen, but something like that does not happen because there are lots of non-uniformities in the material. In addition, to the electrostatic loss of non-uniformities in the material that slow down the motion of the valence electrons. But that is in addition, slows down electrons. These are in addition to the electrostatic forces that the protons in the atom, the attractive electrostatic forces the protons in the atom exert on the electrons. Okay. Overall, taking all of that into account, taking all these forces into account, overall the valence electrons move with constant velocity on the order, it's possible to calculate by the way, okay, on the order of centimeters per second along the wire. Okay, let me take this one out here. Man, I'm getting hot here. Are you getting a picture of that? Okay. So there are centimeters per second. Okay. All of these non-uniformities together with the attractive force of the protons, produce what we call an electrical friction, okay, or electrical resistance. But before we go into that, I gotta go back here, right? This motion of electrons is called electric current. The current from the same idea of water current. Okay, and it can be mathematically defined as, just insert electric current we usually represent by I, the letter I symbol. You have already played a little bit with electric current. You go I, that's how we usually represent mathematically. Man, what is going on here? Huh. I equal delta Q over delta T. If you can count the numbers of electrons that goes through a cross section of the wire, it can be mathematically defined as where the numerator is the amount of charges that goes through a cross section of the wire, of the wire in a given amount of time delta t. Okay, let me erase that. We can here write that if you suppose that you can count the numbers of electrons that goes through there, right? Will be something like that. Ne. Number of electrons is n, electric charge is E. So what you see right here upstairs is exactly delta Q. Exactly delta Q. Another way of representing this current is in differential form. dq dt. That's another way of representing that. Okay. The unit of current is coulombs per second. Coulombs upstairs, second downstairs. This unit shows up so frequently that we give it a name. We call it ampere and abbreviate by the letter A. Okay. All the referred non-uniformities, all the uniformities referred previously. You go. All the non-uniformities referred previously. Together with the attractive force of the protons produce what we call an electric friction or electrical resistance. The electrical resistance depends on the type of material, okay? The length of the material, and the cross-section size, the cross-section area of the material. Okay, so here we go. Let me see if I can show you. Yeah, here's the current. Blah blah blah. Okay, so let's review everything that we said. Here you go. We start with the model of the atom that you're already familiar with from chemistry. Protons at the center, protons plus neutrons at the center. The nucleus is very small, and electrons orbiting this nucleus, this small nucleus. Although the nucleus is small, its mass is it's very heavy compared to the electrons. It's 3,600 times more, approximately 3,600 times more than the masses of all combined electrons orbiting the nucleus. The electrons that are further away from the atom are the easiest one to extract, and they are called the valence electrons. Those valence electrons, what do they do? When you have a material, a metal, in a metal, the atoms are very close to each other. They're forming a lattice, okay? And those valence electrons in those metals, they are capable of jumping from one atom to another, okay? This jumping is random. It's not like in a single direction, but it goes in a random fashion unless you apply an electric potential to the material. If you apply an electrical potential to the material, those negative charges overall are going to move towards the positive side of the battery. Okay. So here you go. We have the copper wire. We have the electrons. And when we apply a electric potential at the end of this copper wire, let's say 10 volts, okay, we produce a uniform electric field in the wire. That's the best way of understanding what's going on. You have to picture this uniform electric field inside the wire. The wire is solid, but there is an electric field in there. Electric fields can be inside a metal. You can have electric fields inside a metal. Okay? And it is this electric field that's going to produce a force to each one of those electrons. Electric fields to the left, electric force is going to be to the right. Okay? And that's the force that's going to power our electrons. One way to picture it is to get rid of the battery, but visualize the fact that we have a buildup of negative charges here, which comes from the negative electrode of the battery, and a buildup of positive charges here that are powering the electrons to the left, to the right, right? The positives are attracting the negative electrons. Okay, here you go. This velocity here is the drift velocity. We call it the drift velocity, and is a velocity on the order of centimeters per second. The drift velocity is on the order of centimeters per second, but in reality, those electrons are flying very fast. The instantaneous velocity of the electron is, hundreds of meters per second. But instead of moving at hundreds of meters per second from one side to another, they're actually bouncing back and forth like that, okay? And drifting little by little towards the battery. That's how we should visualize those electrons. Overall, they're moving very slowly. Okay, and we can define an electric current by measuring, by dividing the amount of charge per unit of time. Okay. What else you have to know? You have to know that when people start to study electric current in materials back in the 1700s, Benjamin Franklin was one of them, they thought that this current, this motion due to the electric charge, they thought that it was due to positive charges, not negative charges. We discovered that it was due to negative charges only too late, back in the 1800s. That's when we first saw direct experimental evidence of the existence of negative charges. Okay? And because we initially thought that the current was due to positive charges, we set the direction of the current in the negative direction of motion of the electrons. Okay? So if the electrons is moving from the left to the right here in this figure, or let's say moving the clockwise direction, the electric current we say that is in the counterclockwise direction. Okay? Current due to positive charges, right? Current due to positive charges, current due to negative charges. So we always set the current as going from the positive plate of the battery. Here you go. Okay, directional flow of the current is contrary to the flow of electrons inside the wire. Okay, here's an illustration of the forces in the electrons, electric force, and the resistive force. The resistance force is due to those non-uniformities in the wire, plus the attractive force of the protons, okay? Here we go. So what do we know about the resistance of the material? Okay, we do know that the resistance is larger when you have a longer wire. The longer the wire, the more resistance we have. The longer the wire and everything else being equal, the larger the resistance. Okay? The thicker wire has less resistance than the thinner one. Everything else being equal, the thicker wire is going to have less resistance than the thinner one. Okay, so we write like that. Here you go. In the resistance resistance is a function of the length of the wire, the cross section, its cross section, and its intrinsic material that we not intrinsic material, and the intrinsic, let we say, intrinsic parameter of the material that we call resistivity. Okay, so what we can say is that a functional dependence. What else can we say? Let's do the equation right in here. Here we go. Resistance is Resistance is a function of the length of the wire, the area of the wire, and an intrinsic property of the wire that we call resistivity. Okay? Like that. And how do we relate that? It's inverse is directly proportional to the area, directly proportional to the length, inversely proportional to the area, and we have this parameter. Again, I'm doing that in a very qualitative way, but it's possible to calculate, okay? It's possible to calculate that. This parameter here, again, depends if it's gold or silver or iron or copper, okay? That's the resistivity that we call. The larger the cross-section area of the wire, the less resistance it offers to the motion of charges. The longer the wire is, the more resistance it has. Okay, so there is also a relationship between resistance, voltage, and current called Ohm's law. I introduced Ohm's law to you in the last lab, right? You plotted a graph, and how does it look like, Ohm's law? It's very easy to memorize. V equal to Ri. The larger the current, the more voltage you need. That's what it is. Okay, you can also, let's write that in a different way. This equation that you see here, Ohm's law, here you go. This equation that you see here, Ohm's law, is the result of the fact that the electric field is uniform in the wire. Okay? Ohm's law. Oh, by the way, it's law between quotes, okay? Because it's not an exact law. Is the result of the fact that the electric field is uniform inside a wire. If the electric field were not, if the E field were not uniform, then this law between quotes, right, would not hold. Okay, that's 5:45 right now. 5:43. Let me take attendance here. And any questions about that? Excel. Good. Lecture attendance. Mario Acevedo. Nope. Toby. Arum. Musa. Genesis Bell. No. Jennifer Camarillo. No. Robert Faust.
Yeah.
Pedro Flores.
Yeah.
Lawrence Flores. Alexander Garcia. Sung Ham. Brian Yes. Athena. No. Dylan Martinez. Rafael Mercado. Alexis Nigret. No. Abraham Perez. No. Ramon Quintana. There. Okay. Ali. No Ali. Kenny Villagomez. Patrick Villavalsov. No. Nolan Williams. I don't think so. So let's see here. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. 12. So let's go break till 6:01 p.m. Okay, 15 minutes. I'll see you in 15 minutes. 15 minutes. Bye bye. Okay, and now we can start solving problems of circuits. Okay, so the samples of all circuits that you're going to see out there is this one that right in here. Okay, we have a battery, a power plant connected to a single resistor. Okay, and so let's say 120 volts, right? Here's this end of the battery, we say is kept at 0 volts. And the positive end of the battery is kept at 120 volts. So negative, positive, so the current should flow in this way, in this direction, should flow counterclockwise. But don't forget, the electrons are flowing the other direction. Your electrons are flowing in the clockwise direction. Because they are negative, we say that the current flows in the opposite direction. Okay? And we can solve a simple problem here, a single resistor is connected to a battery that provides well, a battery of 120 volts. Let me see if I know. Let's say this resistor has a resistor, a 120 ohm resistor is connected, symbol, let's do that again, symbol, here you go, find the current flowing through the circuit. Solution, okay, is Ohm's law. This one right in here, you go. 120 volts divided by 120 ohms. Oops. No. Huh. Try it again. Okay. What we end up having here is a very high current. Those currents, 1 volt per ohm. 1 volt per ohm is the unit of amperes. So instead of 1 volt per ohm, you write 1 ampere. Again, this current is very high, very dangerous, 1 amp. Can kill you. Now let's look at the next one. Two resistors in series. We did that before in the lab. Okay, two resistors are connected in series to a battery. Here you go. Two resistors, let's say 100 ohms. And 200 ohms. Let's put 120. 120 ohms and 200, let's say 200 ohms are connected in series a 10 volt battery. Find the current flowing through these two resistors, okay? Solution. Okay, now you have to think what's going on here. You have to have a picture, a mental picture, what's going on here in this circuit, okay? So think about that. This thing is just a single circuit. Okay, this thing is just a single circuit. So if you put an observer right here at this spot, this observer is gonna see in the gate, right? It's gonna count a given number of electrons per unit of time. But if you do the same right in here, the number of electrons that flows here per unit of time is going to be the same as the number of electrons that flows here per unit of time. Okay. So what do we have? We have this important result that the current is going to be the same in a single branch of a circuit. Okay? So if you connect two resistors in series, they both are going to carry the same amount of current. Make sense? Okay? Let's go back here, you know, because the two resistors are connected in series, they must carry the same amount of current. Well, why is that? Because, you know, suppose that we have oops, more current flowing here than, and less current flowing here. Okay, this current here is going to end up catching up with this lower current here because they're flying faster, right? And eventually they're going to collide with one another. That cannot happen. Okay, you must have the same current flowing anywhere in this circuit here, in a single branch of the circuit. So we can state the following. Here you go. The current flowing through resistor 1, here you go, current flowing through resistor 1 is going to be the same as the current flowing through resistor 2. And that I'm going to call I. Okay, here you go. Subscript. And subscript here as well. Okay, like that. What else can we say about this circuit? We can start talking about the energy of the circuit. You know, remember the voltage is related to the energy. If energy is to be conserved, then this total energy provided by the battery must be split between those two resistors. Okay? So we can write like that too. We can also recognize that the energy provided by the energy per unit of charge, right? Of charge provided by the battery is going to be split between the two resistors, or V must be equal to V1 plus V2. Oh, V1 plus V2. So now we have those two equations. Actually, we're going to have three equations now. We have the following. I1 equal to I2, and I'm going to simplify the notation and call both of them I. We have V is going to be equal to V1 plus V2, and then we have one more equation that we can use, Ohm's law. That's good only to ohmic materials. What else do we have? You know, Ohm's law, right? V equal to Ri. Okay? And that's when we use the equivalent circuit, right? Here you go. We can call R1, R2. Why did I put minus here? Huh, interesting. It's supposed to be plus. Yeah, even better. I'll call it R1, 2. Call that R1, 2 because it's the equivalent resistance. Here you go. That's what that R is all about. Oh man, not responding. 385. Okay, not responding. Good. So what else can we say? We can say that the loss of potential energy across resistor number 1 is going to be R1I, because the current through resistor 1 is the same as the current through resistor 2. And we have the same thing for the second resistor. Okay? So now we have all those equations. Strictly speaking, it was supposed to be R1I1, right? Strictly speaking, it was supposed to be R2I2, strictly speaking. But in view of this relation that you see right in here, we can rewrite that as being R1I. And we can rewrite that as being R2I. Okay? So what we have, 1, 2, 3, 4, 5. We have used this equation. We have used this equation. First we use this equation, right? And then we use this one here. So we now all those 5 equations now are reduced to 2 equations, 3 equations. And we can start to finish our problem. Okay, so here we go. I'm going to use those last 2 equations right in here. And now I don't need, and I can finish my problem now. Okay, so here we go. Go. R1 plus I2, R2. We want to find the current, right? To find the current flowing through these 2 resistors. Okay, so here we go. What we end up having is, and that's what we call resistors, equivalent resistance. So R1 plus R2. When the 2 resistors are in series, they behave as though as a single resistor in which the resistance is the sum. What is the value of the voltage that I gave there? Is 10 volts, right? 10 volts. 120 and 200 ohms. Okay, 10 volts, 120 and 200 volts, 200 ohms. Here you go. And then you finish the math, right? 320 ohms. 10 divided by 320. 1 divided by 32 amps. 1 divided by 32 amps, which is 0.333 approximately. 0.3, maybe more amps. Let's see how much exactly that is. 1.3125. 3125 amps. Okay. So if you have n resistors in series, okay, they're equivalent. They behave like a single resistor with a resistance of okay, here we go. That's equivalent. R1 plus R2 plus R3 plus whatever. Plus Rn equal to summation I from 1 to n. Okay, that's the result. That's the result of Ohm's law. That's the result of Ohm's law. Resistance behaves in this way. Resistance behaves this way because of the relation of Ohm's law. Okay, that's why. And then we're going to compare, Ohm's law with the definition of capacitance side by side. Okay. Now, what about that we did, right? So, what about when you have two resistors in parallel? And now you have to do the same analysis that you did before. But now it's going to be slightly different, okay? Because of the following. Those two ends of the resistor are connected to the electrodes of the battery. They are simultaneously connected to the electrode of the battery. What does it mean? It means that the loss of energy per unit of charge on those two ends of this resistor is going to be V. And the loss of energy per unit of charge of the two ends of this other resistor is also going to be V. Make sense? The amount of energy that an electron loses going from, let's say, this point to this point here is going to be the same amount of energy that a different electron is going to lose when it goes from this point here to this other point here. Okay? And what else do we have to look at? Here you go. The way you look at it is that the electric charge is flowing in this direction, and when it comes to this junction here, just like you have a junction in the road, some of the electrons are going to flow this way, other electrons are going to flow this way. Okay? That was going to happen. It's like having one freeway going this direction, the other freeway going this direction. So we are going to have an initial current that's large, and this current is going to split a smaller amount of current charges here, a smaller amount of charges here. That's how you should picture that in your mind. Okay? So what's the difference between resistors in series and resistors in parallel? Here you go. Resistors in series, four resistors in series, we have the same current, but they have the same current, and the voltage is split in between the two resistors. For resistors in parallel, the situation is the opposite. For resistors in parallel, I believe I talked about that in the lab, right? We have same voltage, and the initial current is split between the two resistors. It's all the way around. Okay, here you go. Let's do the table. We can visualize that better in a table. 1, 2, 3, 1, 2, 3, right? Let's see if it works. Series, parallel. What else? Current, same, split. Voltage, split, same. See that? We have exactly the opposite. Can you memorize that? That's easy, right? Whatever one does, the other configuration does the opposite. Sometimes it can be difficult to adjust this thing. Ah, what a drag. Here you go, like that. Circuit, quantity. Here's the quantity. Circuits in series. For not circuits, resistors, right? For resistors in series, the current is the same. For resistors in parallel, the current is split. You can put like that. For resistors in series and parallel. Like that. Go. Yeah. Go. Like that. So what does it? What happens when we have this situation? Okay. So what does it mean? We're gonna do exactly what we did here. Okay. We're gonna follow the same steps. Here you go. Start with those steps here, and then we make some adjustments along the way. Here you go. Instead of current, now you're gonna have the voltage. The voltage across resistor 1 is equal. Oh gosh. Is equal to the voltage across resistor 2. I'm gonna move that V. okay? And the initial current exiting the battery is going to be the sum of the currents going through each resistor. Let me see if I have a illustration here. Yeah, here you go. I have illustration here. And then that's where we have a split at this junction here. Okay? The sum of the two currents must be equal to this current here, because we must have conservation of charge. Okay? That's how we explain that. V1 equal to V2, right? So let's continue. Okay, we still use Ohm's law, but now I'm gonna use Ohm's law in such a way. Don't forget this R would be the equivalent resistance, and I is gonna be the net current that exits the battery. So we're gonna use Ohm's law again, but now for each resistor separately. R1 is equal to I1, so I don't need to go the next step. V2 is R2 equal to I2. Okay, so here we go. I'm going to apply this first relation here. When I apply this first relation, I get rid of this same relation, right? Once I use the relation, I can get rid of it. Here you go. The first relation becomes V equal to R1I, V equal to R2I2, R1 I1, I2 I2, oh gosh, R2 I2. This one is the, what else can we use? We can use this relation right in here now. When we use this relation on this equation, we get rid of that relation that got used. So here you go. I1 plus I2 is replaced by I in this current. Okay? What else can we do? See here. Let's see if I'm doing everything right. Let's see. Good. Oh yeah, we can solve for I1, right? I use the other relation here. I use this relation here so I can get rid of it. Now what I'm gonna do? I'm gonna solve for those two relations here and get rid of them while we replace in the result above. So how do we do that? We solve for what we do not know. We do not know what's the current, but we do not know what V and R1I are, right? So here you go. Got rid of that. And I'm going to get rid of the other one as well. I2 and I2, R2. Oops. Now I'm going to get rid of that and replace I1 on the equation above. Here you go. Right in here. And right in here. Right in here. Here you go. Right there. What else can I do? Okay. Now we have a single equation. We can factor this value V here, right in here, right? And what else? I can cancel this V and this V. Okay, one, get rid of it. And then finally what we get, this derivation here is more extensive than the other, okay? We can have that, we find out that the inverse of the equivalent resistance is equal to the sum of the inverse of the resistors. Okay, so if for resistors in series we get something like that, for resistors in parallel we get something like that. We get the inverse. Ooh. Like that. Now we are going to revisit what we did for capacitors as well. Okay, so let's summarize. Resistors, resistors. Summarize. Summary. Start with the resistors, and then we put that series, resistors in series, resistors in parallel, resistors in parallel. Okay, and then we repeat for capacitors. Remember what we got for capacitors? Capacitors in series. Capacitors in series was the opposite, right? And then we have capacitors in parallel. Capacitors in series is like that. The relation is like that. Oh, here you go. Capacitors in series. And then capacitors in parallel. Why is that the opposite? Have you noticed that? The relations between capacitors in series is similar for the relation for resistors in parallel and vice versa. There's a reason for that. I'm going to summarize it. Here we go. I'm going to put a table like that, just like the other one. You know, capacitors. Let's see, series, parallel, capacitors, resistors, capacitors. Okay, capacitors in series. Okay, here's the relation. resistors in series. P is the relation. Capacitors in parallel. Here is the relation. Resistors in series. Resistors in parallel. Here is the relation. Oh, what is that? Like that. Do you see that? Inverse, inverse. Proportional, proportional. There's a reason why we have this inversion in the relation. There is a reason. It has all to do is the reason for this inversion has everything to do with the primary relation that led to the above result. And what's the primary relation? Okay, we are talking about the following relation. For capacitors, we are talking about the definition of capacitance, which is Q over V. For resistors, we are talking about the Ohm's law, which, by the way, ends up being V divided by I. Okay? You see what's happening here? Here the capacitance is defined in terms of the inverse of the voltage. Whereas here, the resistance is defined not as the inverse of the voltage, but it's directly proportional to the voltage. That's why you get this inversion here in the series and parallel formulas, because of the voltage inversely proportional to the capacitance and directly proportional to the resistance. That's the reason for this inversion here. Okay, and there is one more interesting thing that I want to share with you. Here you go. Suppose that I'm going to here write this formula here. Instead of writing C equal to QV, I'm going to here write that as 1 over C. Oh, 1 over C, right? It's going to be what? V divided by Q, right? Something like that. Okay? So now we have V upstairs on both equations, right? So let's say we define this term not as the capacitance, not the inverse of the capacitance, but let's say we can define it as being the incapacitance, right? The incapacitance. If you get two incapacitants in series, okay, then you would end up having something like that, just like you have right in here. Okay? Make sense? And there is one more interesting thing, and that we are going to see later on. Remember that I told you there are three important devices in electricity and magnetism, in electromagnetism, in current, in electronics in general. Okay, three basic devices in electronics: capacitors, resistors, inductors, and transistors. Okay, we didn't study inductors yet, but we study half of them. Half of the We are going to study inductors later on. I'm going to here write those relations here in a different way, okay? Let's see. I'm gonna use this one. Okay, I'm gonna write down as Q equal to CV, like that. And then I'm gonna write this one here. I equal to V over R. Okay, V over R. Again, if you were to define that in terms of the incapacitance, right? There you go. I would have written that just in the same way as the resistance, right? And then I'll call that incapacitance. It's possible to define those things, but it just happens that people don't use it, right? What you have here, you have a Q here, right? Even better, I'm going to do like that. 1 over C, okay? That's better. And this term here is that what I call incapacitance, the one downstairs. Okay? What I'm going to here write that, not as I, but I'm going to here write that as dq dt. Okay? dq dt. And now, and this one here for the capacitance, I'm going to here write it not as q, but I'm going to here write as a derivative as well. It's going to be dq dt with one important difference. It's not going to be dq. It's going to be d raised to the 0 power and dt raised to the 0 power. Can you picture that? You know, d raised to the 0 power of q is exactly q. Is no derivative whatsoever. Okay? Then you have the first order derivative, the next step. Do you see a progression here? Derivative of the 0, and a 0 derivative of q with respect to t. First derivative of q with respect to t. Okay? What you're going to see in the inductors is that we have a similar relation, but it's going to be the second derivative of q. Okay? And you're going to have, you're going to see that later on. It's going to be something like that. Okay? DIDT, I'm trying to remember the exact formula. Yeah, it's something like that. Yeah, that's right. It's something like that. Okay? So here you go. Now I'm going to put them side by side. Capata, in strict, if you were to argue in terms of this, what you see right in here, it is unfortunate that scientists defined capacitance instead of something else. Instead of something else that like to call incapacitance, right? It's the inverse of capacitance. So here you go. We have a mathematical progression in terms of derivatives. They are all proportional to V and inversely proportional to the characteristic of your device. Capacitance depends on the geometrical parameter of the device. Resistance too depends on the geometrical parameters of the device plus the intrinsic characteristic of the material. And inductance is the same thing. Depends on the geometrical parameters of what we call the inductor. Do you see the progression, right? Zero order derivative, first order derivative, second order derivative. They are all proportional to V and inversely proportional to the parameters of the device. The parameters intrinsic to the device. It's 6:50 right now. I'm gonna save this thing here, or the exam is gonna open in 10 minutes. You have until midnight to do that. Any questions? Okay. So we can meet again the day after tomorrow. I see you then.
Professor.
Yeah.
So is there going to be a lab on Thursday then, or?
No, we don't have class on Thursday. Remember, just Tuesday.
Okay.
No lab on Thursday, just Tuesday. There is a lab, but it's physics 37, not physics 38. I teach a lab, but it's physics 37, not physics 38. Okay. Here.
I don't know why, but like I can't access the homework on WebAssign.
Really?
Yeah, like I tried the code and everything. It says
What code do you have?
08 something.
Wait a minute, wait a minute. You're using wrong code. You gotta look at the. You go. The code is in the syllabus. Did you look the code in the syllabus?
Yes.
Okay.
0834.
Well, it's not zero. No, it's not 0834. No.
What is it?
Where did you get this number?
It's on the syllabus.
From where?
On the syllabus.
No,
Is it
come on.
course?
Come here. Come here. The class key. You gotta look at the class key. That's the key to log into WebAssign.
Okay. I'm gonna try and log in right now, right here.
Yeah, it's. I do not know why. But where did you get this number? 08. You know.
I'm gonna show you right here.
No, you're using the. Yeah, see, you're using the spring 2021. You're using the wrong syllabus.
Oh,
I do not know where you got that. Yeah, you should get the spring 2022.
okay.
Okay, I do not know where you got that. Get the actual syllabus for the course. 46376888.
4637.
6888. LAHC. So let's start.